So we're extremely pleased today to have Mihai Anitescu from Argonne National Laboratory to give us a seminar. Mihai has been at Argonne since a long time ago. He is a senior computational mathematician working on multiple areas related with computational math, uncertainty quantification, optimization theory, numerical analysis. He's a person to know because he is the associate editor of many SciAM journals, from SciAM DQ, SciAM Scientific Computing, Numerical Analysis, I will assume, and other nice journals in computational mathematics. And he's an affiliated faculty of statistics at the University of Chicago. And today he will be talking on optimization under uncertainty for energy systems. Certainly, the mixing of optimization and uncertainty is a very innovative area with very little fundamentals known, so we're very pleased to hear his views on this important topic.
Thank you very much, Nicholas. Actually, I want to thank the organizer for the invitation and everybody who met with me today for the very warm discussions we had, which I tremendously enjoyed. And thank you very much for coming. So actually, this is the talk which actually, I was not sure what to prepare because I had no idea how many students would be in the audience, so I wasn't quite sure. I know, of course, what Professor Zabaras is doing, but I was not sure what kind of audience I have. So the talk is actually fairly high level, but I'll be happy to answer any questions or deep dive in anything that you find interesting. So I would actually, the talk has two parts. In the first part, I'm not sure how many of you know about energy systems because sort of, I mean, I work quite a bit in it, and it's sort of like, you know, I don't know a lot of people in Notre Dame who do that. So I imagine that maybe I'll walk you a little bit through what kind of applications, what kind of needs an application has, what space it has, and then sort of, you know, how do you model it? And then finally, what kind of a computation do you actually have to what kind of a computation performance do you have to accomplish? And sort of, and then how does the software should look that puts it all together? So I'm going to try to sort of reason about all these things a little bit and actually give you some idea about the space. I put the slide, like I said, I put the slides together from several other talks of mine, so I may skip over them. I'm sorry, but if you feel free to interrupt me at any time and ask me a question, and I'll be happy to answer. Hope to remember to repeat the question. So, all right, so this is actually, a bit of a background. So I worked at Argonne since 2002. At the University of Chicago, I've been tenure faculty since 2012, and I led a project which had about 30 PIs, which started in 2012. And what I'm going to present is work which came out of the work of all these people, which may not involve me as a co-author. It's the sort of work which came out of the project that I led, and actually the project was renewed this summer. And sort of like, you know, it's an entity which has about 27 principal investigators and 20 other people. And I see at least one person, Alex Dowling, who actually used to work, not sponsored by this project, but certainly in relation to it. So certainly it was actually a very interesting entity, but this does not present solely sort of what I've accomplished. In terms of what to expect, sort of like, you know, I'll present you the sort of the broad landscape of the application I'm going to try to attack. But when it comes to what we actually know what to do, it's probably at best 1 or 2% of it. So actually it's very small and very classical. And if necessary, I'm going to stop and explain where things can be improved or should be improved. Right? So this is certainly, do not expect this to be an answer. Right? This is meant to be, this is sort of the kind of stuff you may expect and why it's hard, and it's sort of a tiny portion of an answer, which is hard as well. Okay, so first of all, a few things about the energy system. So typically, this kind of mean the power grid, but not exclusively. So, but I'm going to relate to the power grid because it's the kind of stuff that we all use. You can relate to it. It's easier to explain. So actually, I'm going to sort of focus on that, though I'm going to connect to a couple other things as we go along. So it's a pretty big entity. You see here sort of the shape of the, you see here the shape of the major transmission lines, which are on the order of about 100,000 nodes and lines. Of course. I was trying to get this out of the way, but I was not very successful. So it's actually, so it's something which has on the order of 10 to the 8th components, and actually you're not interested in it statically. You're interested in it dynamically, and more importantly, because a lot of the requirements are of reliability nature, you're actually interested in what would happen if certain combinations of the components here would fail. So the problem has only 10 to the 8th degrees of freedom, but then it has time, and also it has a lot of what ifs. So actually, if you look on that side, it's actually a gigantic problem. Moreover, In time scales, it has 1 e to the minus 16 power electronics to decades in planning. And I'll show you an example where these two scales do come together. It does happen. Okay, so at the very, like I said, I'm not going to read all the slides, but at the very fundamental level, the microstructure, if you want, that I'm going to treat here is going to be a differential algebraic equation where the variables are the rotation speeds of the generators. So that's actually the finest scales I'll ever see. There are finer scales than that, but that is the finer scale that I'm going to refer to in this talk if I'm ever going to refer to it. And then there's algebraic equations which come from the Kirchhoff's laws. So that is the fundamental level, and that is what you see on the level of milliseconds and slightly below that. So that's what you would see. What is interesting about it and why it is optimization is that people use optimization when reasoning about energy systems at multiple levels, which again range from seconds to decades. And this is a few things that they look at. For example, they may want to decide whether to beat a transmission or a line or to add a generator. That's called a planning problem. The planning problems tend to look about 10 years ahead, sometimes 20, sometimes 1, but they're on the order of years. Then there is software which run to actually to run the markets, as they say, and I'll come back to that. So there's a number of functions. All of them are optimization in nature. I'm not going to read them because to some extent I will not have the time to explain them anyway. But actually they go from the space to daily to minutes. And markets are run by software in this business, and I'll come back to it. And then you have stuff which is much more on the control level, which is again optimization problems on much shorter time scales. So here you go from seconds to minutes. AC power flow, it's run in minutes, and actually this is an extremely common analysis. I may come back to it. State estimation run every 1 or 2 minutes. Generation control is run in seconds. Voltage dynamic stability is run in milliseconds. So this is, all of these are optimization problems. Let me come back to markets. So normally you think about a market as a place where people go in front of the board, they bid, and then of course they accept the bid or they propose the different bid. And then there's the transaction. In energy systems, it cannot happen that way because you're limited by the physics of the network through which you transmit. So just the fact that somebody offers power in North Dakota is not sufficient for somebody to buy it in the East. So in order to actually run the market as a response to the bids, you have to run an optimization software which certifies that the solution is both feasible and safe, secure. So that's why it's a market run by software. It's not run by the bids themselves. So actually you do need to run this software, this optimization problem, in order to just decide what the locational marginal price would be. What is the price at the node of production or distribution? So that's what makes the grid special, because of the connection. And because of the fact you cannot store electricity, not easily. So let me give you sort of an example of one problem first. So this is a transmission problem. This is the transmission planning problem. So this is its upper level. So the upper level, what you're trying to do is that you're trying to minimize some sort of economic quantity, say the expected cost of the electricity production. So that's not exclusive, but just to think about something. This expectation is random with respect to, for example, it could be with respect to prices, but it can also be random, more importantly, with respect to energy production levels if that production comes from renewable energy. And I'll come back to this point. And then you have some sort of a discretization of the equations you saw on the previous slide. And then you have some, of course, path constraints, normative constraints. But then you also have, to some extent, uniquely to electricity, regulatory constraints. And the regulatory constraints are about safety. They say, if something occurs, your system should be able to get in this point and no worse. So this is how they look like. So typically those are, so that problem I showed in the previous slide has a horizon of 20 years, of 10 years. I'm trying to minimize the expected cost over 20 years. But with the constraint that if at any point during that time, some sort of event occurs, meaning that, for example, you have a short circuit. So one of the most common short circuit sources in this business is actually squirrels entering substations and getting fried. So sort of like what happens in that situation is that there's going to be an overcurrent. And then, of course, there's a protection relay. And the protection relay actually takes the line off for a while, hoping that that will clear, and then tries to reconnect. But what could happen is that in the period between disconnection and reconnection, you may actually get the system unstable, and you may trigger another event. And then you trigger what's called a cascade. So you want to prevent that. To make sure that doesn't happen, at any point in this transmission plan of yours, which has 20 years, you have to actually sort of virtually add this event and see whether the system in that particular dispatch schedule was able to clear it. And that has to be done dynamically, and the time scale is the time scale of the generator, which is milliseconds, right? So actually, at any point, you have to run a millisecond simulation with these what-ifs to decide whether that is a safe dispatch rule. Okay, so if you were to put everything together in the planning problem, this is the planning problem as it's solved today. If, for example, if your Citizens Utility Commission gets a request for rate increase because you need the transmission line, this is the process they go through. They have to solve this dynamic programming problem with these transient constraints, which are induced by the possible what-ifs. And that is a true simulation. Of course, it's not run that way and that is one of the sources of uncertainty, and I'll come back to that, because of course direct transcription of the problem requires 10 to the 26 variables. So in our lifetime, this is not going to happen, right? So then what people do is that they approximate this problem in a number of ways. For example, what you do is the previous problem is a long horizon optimization problem, so you run it without a network. So effectively what happens now is that people say it's too big of a problem to solve. So what they do is that they start to make a series of approximations, and typically these approximations are declared to be correct based on an individual who says yes. There's actually not a procedure which requires a certain metric to be satisfied. It requires somebody to sign off on it. Right? So certainly if one thinks about doing uncertainty quantification of this reduction, that's not a place where the industry is at the moment. And of course, and that's the pitch here, it's a place where you'd like it to get. All right, and actually this is current practice, and I'll explain in a second that things are changing. So this is what you have to solve today, and to some extent don't. So this is an estimate which I've heard. So an estimate which I keep using in my proposals, of course. So there's an estimate which actually says that the US, let me come back to this in about 3 slides. But keep in mind the fact that you end up with a problem which is too large. An individual reduces it and then provides a solution by brain. And that's where it's at. I'll come back to it. So this is actually a fact, right? So the grid operates cheaply and safely, actually. So US has one of the lowest electricity costs in all of the Western world, right? So this is not expensive, right? So it's actually cheap and safe. Even when there's act of God, we're typically okay. As I said, historically, there was a separation between analysis. Certainly, direct transcription is beyond any compute power by 2050. So it's not in the cards. So we'll have to do something else about it. And as I mentioned, the way this is done is by engineering judgment and offline reduction. So, for example, when you do transmission expansion planning, the scenarios that you use that should be random are done by judgment. They say, I'm going to just compare these 5 lines, because in the past 30 years, those were the options available. Typically, what happens, and I'll come back to this point, static constraints for cost contingency states, again, in a couple of slides. And you do screening of the contingencies. So you know that, say, 1 million things could happen. You decide which are your top 20. And then you decide whether you're safe only against those. Recourse is generally implemented with operator in the loop, meaning that although there is the potential to automate the response to an event, that's not the way it runs. So there's 2 levels. There's the level of control. So at the level of frequency oscillation, that's actually done automatically. It's called automatic generation control. So below a second, that's done automatically. But the 30 seconds response, if, for example, say you have a generator that goes down, that's actually done by a human. So a human interprets in a screen something and then sort of modifies to issue a dispatch control to the reserve, which is actually dispatch, but it's not automatic. It's with a human in the loop. You'd think it is, but it's not. It's actually with a human in the loop. Okay, so while perhaps dated, it has served the model well. Like I said, US has one of the lowest electricity prices and high reliabilities. Though here it does deserve a caveat. So the US reliability, which is measured by the average downtime per customer, is 10 times larger than Germany's. So it's true that the German electricity is 3 times more expensive. But the average downtime in the US is 10 times larger. Right? It's certainly not as India, which is known to have one of the more difficult reliability issues, but it's not great. It's okay, but it's not great. But certainly, we don't run around in darkness, right? So the system seems to be okay, right? and it's not expensive. So, but of course, one of the issues anytime you do research and development, you try to tell the people, we haven't solved this problem, right? So it's the typical pitch you make when you remind people that they've just done good enough, but things have changed, and you may want to do something else. So let's look a bit at the evidence. So actually, these are 4 snippets, which actually I collected from sort of public, news outlets. So there was the 2003 blackout, which affected 50 million people in the Northeast. I'm not sure how many people were around and you felt it. I was in Cleveland, so I felt it. So a year after the fact, they came up with the report, and they said the following. We could not complete the simulation in the 6 months we had available. So actually, the report never figured out exactly what happened, because they couldn't run a dynamical simulation for something which took 10 minutes on a 1 millisecond time scale. So just to put things in perspective. The 2013 Super Bowl blackout is a really good one. So after the fact, they said manufacturer blamed the Super Bowl outage on an incorrect setting. So what turns out that had happened is that somebody set incorrectly the relay, which actually protected the line from the energy operator to the stadium. In 2014, there was the gas shortage curtailment in Texas, and I might come back to that. And this is actually, this is my favorite one, the 2015 blackout at the White House. So that is my favorite one, I have to say. So they said explosion at power plant responsible for DC area outages. So as I'll explain, the federal rules require that anytime you declare a dispatch, meaning that you tell each generator how much to operate, it has to be done in such a way that if any one event occurs, then you're going to be able to recover from that, or somehow you're going to be safe against it. What happened is, in this case, in the calculation, it wasn't. What I found out for the fact is that what happened is that they had a double event, which was labeled a single event. So what happened is that they had a substation that actually, if it blew up, it will take off 2 lines and not 1. But when they analyzed it one at a time. So they declared it safe, but it wasn't. So this is a, so you would argue, and this is certainly I would argue, that based on your ads, certainly electricity, though it seems to be contained in the sense that, well, there it is, it's on, we plug in, it's fine. It's certainly not a solved problem, but how's that possible, right? Because it seems to run fine. So the reason why that's possible is that there's multiple levels of reserves which pick up when you make an error. So for example, there's a spinning reserve, which is at the 10-minute level. There's a non-spinning reserve of 30. There's a replacement reserve of 30 to 60. All of them are operator controlled. So when something's off, which is your simulation, so what happens doesn't do what your simulation told you should do. Somebody goes on and fires up another plant. And it's done, like I said, by an operator. Of course, these are off-market decisions, meaning that when somebody does that, they're not concerned about what is the cheapest action. They're concerned how they make sure on their own authority that it gets to the place they want them to get, which means that we don't know how much this costs because we're not running it against the best estimate. So there's estimates. For example, people estimate that this costs about $20 billion a year, right? So the price you pay for this lack of precision is the fact that you're going to have a higher operational cost. We don't know how much it is because we're not running it optimally. But what it's estimated is about $20 billion a year. That's a pretty big number. Okay, so this is an example about how you may actually create the margins, or you may create the errors, which actually make you lead to either the wrong conclusion or the incorrect dispatch, meaning the incorrect generation decision. So typically what happens is that because of the approximation, when you try to reason about the consequence of an unusual event, you're actually going to reason about it as steady state. You assume that it's a transient and it's resolved, and after the transient you try to make sure that the voltages are in a position you want. But that's not what really happens, because what really happens is that once that happens, you actually initiate a transient, and you want to be sure that during the entire duration of the transient you don't get in the wrong area, because getting in the wrong area meaning that you're going to get somebody else to be overloaded, and they may trigger their own breaker, they may take that line off, and that can actually continue. So typically what people do is that they do this instead of this, or I would say instead of this plus this, and they play with the bounds here to actually make sure that the solution to this is actually feasible once you get the transient. When you do that, you introduce what's called a margin, which means that you introduce an engineering sort of margin of security, which you need it only from time to time, but you're going to pay for it all the rest of the time. So it's these margins that's estimated to produce this cost of $20 billion a year. And this appears, like I said, primarily from an approximation which is not structured properly. This is typical. The way this is done is that people run this analysis many transients offline, and they decide what is the limit here that would make all this feasible. And then they impose it for the entire year. And then they do it again the next year. Right? But of course, many times this was actually not necessary. If you'd have enough computation, you could actually fix this in real time and pay less money. Right? That's how it goes. This is where the money goes. So, and that's why it works too. Right? So the money's in here. Right? Okay, so I'm not going to discuss about this. So, and actually what's remarkable is that that's the situation today. Right? So if you, today, with today's energy portfolio, that's what happens. We actually under-resolve a problem which goes for $500 billion per year industry, and that all of us are affected by. It's actually under-resolved. But with the margin, you hope that it's okay. And it has to be, though, as I mentioned, we're 10 times worse than Germany. Right? So, if you think that's okay, but those are the facts. But we want to change everything, right? Because, for a variety of reasons, we'd like to actually get a low-carbon future. Right? So in a low-carbon future, what we hope is going to happen is that we're actually going to remove from single-directional to bidirectional floors. We assume we're going to have energy storage. We're assuming that there's going to be a lot more renewable energy, renewable power at the customer, which means that it's in a load area that you actually do not control as a utility. Right? So you have no idea if somebody puts solar panels on the roof, how they configure them, how they're going to use them. Right? So actually, it's outside your control. So you're going to get a lot more wind power. So as I argued, today we get things that we don't expect, and now we want to change everything, right? So it's likely that may be a problem, or it's certainly a hypothesis. So this is an example. So for example, this is a small study I did with a postdoc of mine. So for example, what you see here on the top are the typical demand levels in the Chicago area. So those are you cannot see it very well. So these are the curves at the top. And what you see at the bottom is what they would be with if 20% of Chicago would actually get this energy from solar. So what you see is that all of a sudden, particularly in the middle of the day, and that's actually a very known factor, in the middle of the day, you're actually going to depress the demand, and it's going to come back roaring towards you at night. This is called the duck curve, by the way. So two things will happen. First of all, you're going to depress demand in the middle of the day, and then you're going to have to ramp like crazy towards the end of it. So that is a known factor. So there's multiple, that in itself actually, may have a 30 minutes discussion, which I'm not going to have. But the more important thing is that actually, if you use the same techniques that you normally use to forecast demand, you're going to be off by a factor of 2 in terms of the error, right? So which means that you're going to consistently under or overestimate how much power you need by a factor of 2, which means again, you're going to have to make your margins even larger. So you're going to have to pay more if you want to stay as safe. So most likely, it's going to cost you more. So of course, one of the things that actually the US is famous for this could say, but we may still be lucky, right? So this is sort of like, having worked for the Department of Energy for 16 years, you hear this a lot. So actually, let's look again at the German example, right? So Germany is famous for the fact that actually it went very aggressively towards solar power in the last 15 years in particular. So what is less publicized, they also went up a lot by the number of control actions they had to take at the third level. Remember that when I showed you my reserve stack, I showed you 3 levels of reserve, and at the top one was the 30 to 60 minutes one, right? If you need to use that reserve, it means that you have nothing else after that. If something else happened, you have to cut somebody off, right? So you have 3 levels of reserve. This one you use when it's okay, this one when it's a bit hot, and use this one, and if it's not sufficient, somebody has to go on blackout. Right, so the number of times you use the third level reserve, it's an indicator about how close you may be to a dangerous situation. So in Germany, they went from 2 such events in 2003. This is one of the operators, which is called Tenet. They actually went from 2 such events to 1,200 such events over a span of about 10 years, which was coincidental with the increase in renewable power. So it's plausible, though that's not a proof, that part of that was due to the incorrect forecast in electricity, right? It's not, of course, this is not a proof. This is correlation. Doesn't imply causation. But still, it's certainly unlikely that nothing will change or will have to. And this is actually evidence how that could come about. Then there's the increase in the natural gas, but I may come back to it because I see that I'm 327, which is a lot. So, and I want to go to the second part of my talk. So this is the message, right? So it's a system that we don't understand sufficiently well. We certainly cannot solve at scale, but which we want to change completely because we want to give more say to the consumer, how they operate. We're going to have a significant increase in uncertainty supply and demand. We're getting an increased reliance on distributed generation natural gas. We're getting changes in power flow patterns because of the new wind plants. We get increased dynamic ranges. The example of that long ramp that I showed you, it's an example. That's called the duck curve. You get new devices, etc. So all of them point to change in a system that we still perhaps don't control as well as we should. So I'm going to go over this one. So we have a complex system which we don't operate optimally, which we aim to expose it to more outside variability. So with my colleagues at Argonne about 6-7 years ago, we started to think about how do you create an energy management system which deals with both these issues. Okay, so that's motivation. So at the moment I'm going to refer just to ambient condition uncertainty, though as you just saw, the amount of uncertainty in the approximation itself, it's unknown, and that may be the bigger factor. But of course, it's also mathematically harder to tackle, I would say, in terms of manpower, right? So there may be even bigger sources, but because everybody's excited about putting more renewable energy, and certainly that's what the sponsors want you to do, then that's one of the questions you have to address anyway. So then one of the questions is that how do you accommodate more solar and wind power on a grid which is already potentially stressed? So I'm going to go over this and just say that, so now you're changing things quite a bit, right? So you want a different energy supply, right? So you'd like more solar power, and you want sort of more wind power. And those are not dispatchable, meaning they're not under your control, right? Those do what they decide to do. So actually, and this is some idea. This is the variability in solar power. And this is a bit misleading because of the scale, but this is a good one. This is over 120 hours. So this is wind profiles, right? This is what the demand would look like, and these are the wind profiles. So as you see, from time to time, wind goes from a high level to almost zero for half an hour. Now, if you base yourself on wind power, that's a gigantic problem, right? So many times it has variation which are not as bad, but once in a while, it drops altogether, right? So most likely, and more importantly, if you certainly in a data-oriented kind of approach, this is not be foreseeable, right? So something like this would be difficult to foresee based on data, right? So it means that you have to somehow accommodate the fact that you're going to have an uncertain power supply with a potentially very high variability. Okay, so then the proposal is to actually use a controller which is based on optimization or stochastic optimization to actually deal with the top level problem that I showed you before, which looks like the planning problem, to actually do effectively the optimization at the level of the financial dispatch, meaning it takes in the price signals for the resources and it decides how much to use over, say, the next 24 hours out of each resource. Then it sends set points to the lower level system, which actually is the thing that actually changes in real time the settings to answer for other things, such as micro disturbances and such. And then, of course, you send this information to forecast when you get a weather model as well. And then you return to stochastic optimization. And the hope is that if you have very advanced forecasts, you can hope to be sufficiently proactive about your optimization that you're going to be able to maintain the system to be safe and at the same time to do it as cheaply as possible. So that's the idea. And that would be done because I solve a minimal cost problem here. So this is the idea. So you switch a deterministic problem to a stochastic programming problem. And of course, I mean, sort of like, this is a schematic that I'm sure you guys have seen before. So typically, this is considering current dispatch. And what people do is that they use just a deterministic control solution based on the mean, most likely. Right? So that's when we're going to compare against the deterministic solution. That's what's going to happen because this is the current practice. And of course, what we're proposing is actually to move from a deterministic version to a stochastic version, assuming I have an advanced forecaster in the loop, which in the case of weather most likely involves a weather code. I may come back to, so actually I have these slides at the end, but I may not get to them. So weather forecasts by data are actually famous for being not reliable over 2 or 3 hours ahead. So you pretty much have to use a numerical code of some kind. So if weather is your concern, then you must use numerical simulation for weather prediction, which assimilates data. And if you need uncertainty, you can actually have to sample from the filtering distribution. Right, so this is if you guys have done Kalman filters, it's the same general idea, except that the system is very, 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 very big. Or it's the same idea. Right, it's to some extent, how you would do efficiently Kalman filtering. So that in itself, how you do it at the resolution you need, again, would deserve its own conversation. I have a few slides, but I may not get to them. But I'm going to focus rather, I'm assuming that somehow I produce high quality samples of weather, which tells me with fairly high accuracy what is the probability density of having a certain amount of solar power at the place I have my panels. And then I'm going to focus on the second part, which is that how do I solve the optimization problem which is related to that. So that I'm not going to focus on how this is generated, though again we have done quite a bit of work on that, and it does involve running what's called WRF, the Weather Research Forecast Code, how to sample it, etc. But then somehow I get my samples, and then I focus just on solving this optimization problem. Okay, so then sort of my primary problem is going to become what is called a two-stage stochastic programming approach, which is, as I mentioned, actually to somebody, so let me read it first, and I'm going to ad-lib about it in a second. So the idea is that somehow you have scenarios. For the purpose of the discussion I had here, assume the scenarios are different possible outcomes of weather, like solar power high tomorrow at 3, solar power low tomorrow at 3. And the probability is 70% for the first, 30% for the latter, for example. Of course, you need a lot more samples, hundreds to thousands, but that's the general idea. So somehow I generate my samples chi, and then I want to minimize over the decision, which is, like I said, the typical decision that you have to make is the dispatch decision, meaning for the dispatchable resources, which is coal plants, gas plants, nuclear plants, what levels you schedule them to run over the next 24 to 48 hours. And this you have to change every hour or so. So U is this decision, U is this dispatch decision. So the moment I'm going to be worried about only how my dispatch decision is done a day ahead. So it's going to be a constant. I'm not going to change it every hour. So this is sort of, it's called the day ahead decision. So, and if I look at it that way, then this ends up being, and the minimization is not just over U, it's also over Y, which are the dispatch level once the wind actually gets instantiated itself. So then you get actually this, you actually get this, you can assimilate it like that to make it simple. So you actually get what's called a two-stage optimization under certainty paradigm, where you assume that you have a first stage decision. So let's say to make it simple, so typically the first stage decision matters for plants which are slow to change. So those plants are, for example, coal plants. So coal plants, you cannot change their setting very easily. Well, heck, nuclear plants are even harder to change. You don't change them for months. But let's say coal plants, which change 24 hours ahead. So for a coal plant, you have to decide about the day in advance what level you're going to keep them at and what schedule it should be. So that decision is done for me a day ahead, irrespective of what the wind power is going to be tomorrow, which may change whether I need more or less of it. So the settings of the coal plant become my first stage decision. And then the adjustments which are done to the fast generators, which are, for example, gas, become my second stage decisions once I see how much wind power I have in plus or in minus. So that's why this is called a two-stage stochastic program. Now, it's not the best paradigm for decision, because in reality, that's not how you decide. This is how it's run. So for example, what's called unit commitment, which would have integer variables, this is done a day ahead, and then the schedule is not changed. So this is a fairly correct paradigm about how things are run today. Now, there's not the way you should do it because you keep getting new information, and you should adjust this. But in reality, we have not formulated, I don't think, in this area, how uncertainty should interact with decision if they're done sequentially over, say, 24 periods. Right? That formulation doesn't even exist. So this is not the right formulation. I'm not pretending that. It's just a support for reasoning about how you may respond to a probabilistic uncertainty in the case you have decisions you can make in the first stage, which is, like I said, the dispatch of the coal plants. Okay, so it's not the perfect model. Now, this model is extremely common in financial industry, so it's used a lot. So in terms of who uses stochastic programming in industry, is the financial guys. This actually has not made it to be so common in this area. So this is actually, I would say, still at the research stage. Okay, so I had this, and it was a very interesting topic, but interesting on time. I'll actually skip it. So before we, so maybe I'll just spend maybe 2 or 3 minutes on it, just because this is actually the part which is the really technical one, except for the computation one. So in doing that, there's 2 parts to the problem. So one part of the problem is representing the probabilistic information. That's where the linear modeling goes in. And the second part of the problem is solving the optimization problem. So the probabilistic modeling, actually, it's quite complex. So I'll give you just a few small examples. And the probabilistic modeling, other than the wind forecast, actually even the wind forecast. So the wind forecast, you can use WRF, but that's a problem. Let me explain. So for example, so this is actually something which I wanted to mention. So people are not using probabilistic modeling. We're making this decision operationally, but there is a big push for it. So one entity which pushes for it is FERC, which is called the Federal Electricity Reliability Commission. So actually, they're trying to convince the utilities to use software which allows for them to deal with the uncertainty from wind and solar. So it's not yet at the level it's used. They're pushing them. So, however, it's not what is done at the moment. So this requires to model weather, demand, sub-second noise, fuel cost, reliability. So actually, if you want to go probabilistically, you have a lot of work to do. So in the interest of time, I'm going to show you just one issue with weather. So each of them requires its own mathematics. There's not enough time to discuss each of them, so I'm going to choose just one. So here's an example, right? So one of the problems is, this is one of the things that still has to be done. So you can do the following, right? You can take something like a forecaster code, like the weather research forecast code, and try to forecast conditions for tomorrow. This is wrong on 2 grounds. Number one, the weather research so this is an example where you actually have to do mathematical modeling to get the right outcome. So it's just going to be one example. So first of all, the weather research forecast code gives you information on 25 kilometers to 20 kilometers. That's useless for the purpose of forecasting on something which has spatial scales of 100 meters. Right? So you must interpolate that information, and if you want to do uncertainty, you have to understand how much uncertainty you have when actually the solar plant is in between the grid points of WRF. That's number one. Number two, WRF itself, it's not a great code in terms of predictive power. And so I have this wonderful discussion today with a colleague in ecology and evolution. So actually it turns out that, for example, WRF consistently misses things like temperature and wind speed above lakes. Right, so on top of having the uncertainty of the fact that you don't know what the grid you're predicting with, which is something which is sort of something you can deal with mathematically, I mean, you're using something which is a black box, which you know it's wrong, but you have to fix it somehow. So one idea, which is actually sort of fits, I think, quite well with Nicolas's vision of how to integrate data and models, is actually to use data, historical data, to understand what kind of error you would have in WRF and when. And then so once you understand what kind of error you have, then you make a forecast with WRF. And then if you have the error distribution that you fit it, you actually can do a conditional prediction based on the forecast of WRF itself. So what I'm going to do is that I'm going to take WRF and I'm going to fit the error model from real data. And then operation, I'm going to do one WRF forecast. And then using this model, which actually gives me the correlation between the WRF forecast itself and the actual happening, I'm going to predict the actual happening. So this is a hybrid model which actually puts together observations and numerical weather prediction. Right? So you have to run both. You have to do machine learning or whatever, let's say statistical analysis to feed the model and then use it. Okay, so then that's what we do. We actually do the Gaussian process model. It turns out not to be a terrible idea. This is about wind speed. Remember, I want to get wind speed because I want to know how much wind power I have. So of course you would say Gaussian model wind speed. It turns out not to be a bad idea because of course we're in the Midwest. We're blessed with a very strong prevailing wind. And actually if the wind would be zero, it's a problem. Right? But if you have strong prevailing wind, you can approximate the oscillations to some order Gaussian. It's not such a big deal. Right? Okay, so then what we observe is that particular around, so this is actually my first city of Chicago. So like I said, particular around the lake, you get improvement in the forecast by about 60%. So it's significant, right? So certainly you actually can improve things by a lot. And like I said, most likely if you want to use something like the weather research forecast code for prediction of solar and wind power, you have to correct it statistically somehow. Because as I said, it's not on the right scale, it doesn't have the right physics. Right? So this is just an example about the kind of sort of things you have to do after the fact to fix things. So this has its own mathematics. I'm not going to go any deeper than that. I just wanted to give you an example of the kind of modeling which is required. So we have like 8 or 10 other such pieces that we model, but I just wanted to give you an example. Instead of doing that, I'm actually going to skip over very interesting questions. Yes, this is something I have to show. Right? So one of the questions you get always, like I was talking to Nicolas, is that what good does this do to me? Right? So why should I move from a classical control paradigm to this advanced control paradigm when I have to go to the plane of running WRF, then statistical modeling, so stochastic programming? Why? Okay, so what we decided to do actually with my this is actually a fairly old slide, which was done with my colleague Victor Zavala about 4 or 5 years ago. So actually we looked at the number of systems to actually see what kind of benefit that would give you. So actually this is an example of a photovoltaic system which is actually attached to a residential unit, and it has its own storage which is based on a fuel cell. It has an electrolyzer. So actually it looks fancy. At the time we're designing this cost about $40,000. So for a residential building of 6 apartments, it's not impossible. Right? So it's not out of the realm of possibility. It's expensive, but we're not talking about $1 million. Right? So and this was price of 5 years ago. Right? So this is certainly what is plausible to run. And right, so we ran exactly our methodology. We did the same thing which I mentioned with the solar radiation, and this is actually what you observe. So what we did is that we compared the nonlinear model predictive control in stochastic version, which is what I've shown you before for 1 hour, 2 hours. This is infinity, 14 days. So what you see is the benefit of taking a very reactive approach where I actually do the classical closed loop control versus taking the financial long time approach where you actually model the problem I told you, where you actually model the dynamic and you do the dynamic program which deals with that. But again, the uncertainty appears only in the first stage. I don't do multi-stage uncertainty. I don't know how. Right? So I know I'm going to make multiple decisions, but I'm going to consider the uncertainty only once. I know it's a problem, but this is the best I can do. So what you observe that even with this limited method, if you have, right, so what you see here are how much more expensive, by how many percent you're more expensive than the optimal solution. Yeah, at about 14 days, if the horizon of your dynamic program is 14 days, beyond that you don't get anything more. That's it, it's the end of it. But the other extreme is an hour. So in an hour, the solution is 4 times more expensive than in 14 days. You don't need 14 days, a day is about right. Right, so you don't need to solve a problem which is that expensive, a day is actually sufficient. But we're talking about costs of 3 to 1 or 4 to 1. If you don't use uncertainty or don't consider uncertainty versus you consider uncertainty. And where it comes from, it's here, right? So what happens is that once in a while, the deterministic policy will fail to satisfy the load. So you're going to pay a very high penalty for disconnecting. And that's actually a known fact. The penalty in the US is about $1,000 per megawatt. It's standard. So that's what's going to happen. So that's going to be very costly. I have an example with thermal storage in a building. very similar results, I'm actually going to move directly to computation. So the summary of this part was the fact that for me to do stochastic programming, I have to model stochastically. I certainly have to model the uncertainty somehow, right? If you think about weather uncertainty, that's a famously difficult problem, right? Most likely you'll run something like weather research forecast code, and even that is not going to do it. You'll have to fix it, right? So this is just an example of the work. There's issues about uncertainty in the initial state of the system. There's issue about uncertainty in the frequency. There's issue about the uncertainty in the models you use. So it's big. But I'm just giving you just one. And each of them has its own mathematical challenges. I'm just showing you one example, just the one I've shown. OK, so supercomputing, which is actually what I promised I'll tell you. I'll talk about it in the last 10 minutes. Talk about false advertising, right? So this is actually one of the parts which was the most frustrating. The reason why I started it is that I work in supercomputing at Argonne, always did. And one of the things was like, when I looked at this problem, I was like, there's no way these guys can solve the problem without having a supercomputer. So it's just impossible, because there's many what ifs you have to run. And now that you add uncertainty, there's a lot more what ifs that it has to be true. So I would say that the reality is that parallel computing is starting to make some inroads, but the use of supercomputing is rare here. However, it's quite probably will cost less than using humans for scenario screening. So for example, if you do the calculation I've told you in the beginning, you actually end up with a gigantic problem with a million scenarios and 10,000 degrees of freedom. And this is only an RTO area, which means that I'm neglecting distribution. I'm assuming I have, so each distribution node, which is say all of Notre Dame, is attached one impedance element, which is a pretty big reduction, right? And I'm maintaining only the backbone. And when I do all that, I end up with this. So it's still big. So certainly it's a question, the question is that if I'm going to move from a deterministic decision paradigm to a stochastic decision paradigm, all of a sudden the scenarios have increased by a lot. So is that doable in the time scales we're talking about? What time scales are those? So typically when you solve such problems operationally, you have to come up with answer in about an hour. So that's what it means real time here. So you have to adjust for the next if you adjust the call levels for the next 24 hours, you have to come up with the decision in about an hour, not a minute. So so that's what real time means in this setting. There's discussion about changing everything, including the 1 hour to a minute, but at the moment let's just say it's an hour. Real time is an hour for me. So let's talk a little bit about algorithms. So when you solve a stochastic programming problem, it has this tree structure, which comes from the following observation, which is that you have a first stage model which tries to account for all the possible what ifs. And then if one of the what ifs occurs, you have a second stage decision. For example, the first stage decision is the coal plant, and the second stage decision is the fast gas plant. But what happens is that if I know where the coal plant is at, which is the first stage decision, all the other problems are independent. But they're all connected through the first stage decision, right? So the first stage decision, which is the coal plant, must account for all possible outcomes. That's where the trivial parallelism, non-trivial parallelism comes from. See, if I wouldn't have this would be just a task parallelism, right? You can run whatever you want. But the fact that they're connected through this, and I must find out the optimal one subject to all the possible outcome in the second stage, is what makes the problem difficult. It turns out that, of course, unsurprisingly, machine learning has the same pattern. But in machine learning, typically, the first stage problem is not large. Here, what happens is that the first stage problems can have on the order of 10,000 to a million variables with the network constraints. So it's a non-trivial pattern. And you may have something like 10,000 scenario here to 100,000 scenario here with about the same size of the system as here, which is, again, somewhere between 10,000 and a million. So that's where it's different. Right, in machine learning problem, though not exclusively, you may have thousands of parameters, but not millions. Right, so that makes, so for example, where is the difference? For example, if I have a 1,000 by 1,000 first stage matrix, it's a matrix I can store in memory, even if it's dense. So I can do something like BFGS, no sweat. If it's 1,000,000 by 1,000,000, I can't. Right, so that is a huge, I pretty much have to go off one node. Okay, so so that's why there's a big difference. There's no way you can do this efficiently without doing some parallelism. It's impossible. So okay, so let me give you an idea about linear algebra now. So typically what happens is that you solve the problem I showed you in the beginning by what's called interior point algorithms. I cannot tell you much about it, but the important part is that the linear system, once you have the scenarios, has the famous arrow-shaped structure, which it goes like this. So this is the part of the Hessian of the Lagrangian of the problem, which corresponds to the first stage decisions, and it's connected to all the scenarios. But see, if I know this variable, which is the variable attached to the first stage problem, then all these other problems are independent, and I can solve them by just doing diagonal pivots. Right? So if I were to eliminate the last row and column, the problem can be solved in parallel trivially. So what's going to happen is that sort of like, what you'd expect, which is that you will try to solve the problem starting from the upper left corner, and you can actually eliminate this block perfectly in parallel by just computing the Schur complement, which is this part, in parallel, and then you're going to assemble it all here, and then you're going to do this with you're actually going to do this with a dense solve. So you have this trivially parallel part, which is where a problem is going to come in, and you have to be sure that when you factor this part, you actually do it in a time which is fast enough that you can leverage the fact that you have lots of scenarios. So this requires a lot of innovations. So it requires multi-threading and full sparsity exploiting. So one of our solutions was the fact that, for example, you want to solve the Ki sparse, but you have no hope of doing it dense. So this you have to do multiprocessor, but the important part is that this Ki, which is sparse, has a lot of back solves. Right? So normally people tell you take Ki and factorize, then you're going to do one back solve is done. But here Bi is on the order of Ki. So just the fact that I have sparse factors may not help me. So what happens is that here you actually expose the sparsity in Bi itself, and Ki is changing. So one of the tricks that we have been doing is actually to do a symbolic factorization here, and then keep it in memory, and then use this by correct the error by using BiCG stab in order to leverage parallel computing. So the idea is that you do this analysis once, and then you do BiCG stab, and actually this can be done in parallel because you can do column by column. So there's a couple more ideas. Anyways, at the end of the day, we do have an algorithm. So this required quite a bit of number of innovations. So at the end of the day, we do get something which scales linearly, and it's all in the linear algebra. It's all by accelerating this part. So we do this on 30. So this particular architecture had 4 cores per node. So this is more than 100,000 ranks. And the important part is actually that we do get linear scaling, close to it anyways. So we do scale quite well with the number of scenarios. And as I said, the trick is actually to hide I'm not talking about how I'm doing this. This has to be done densely. The trick is actually to hide the cost of this by parallelizing it and make sure that you optimize the scenario solves. So I'm sort of tight on time. So actually, if you don't mind, I prefer I end. I'll just say one more thing, which is that one of the things that we actually ended up doing, and I'll just read these slides on the last slide, and then I'll answer to any question. So one of the things that actually we understand in optimization systems is that what you tend to lack many times when you get an application is a very high level representation of your system. That's why we love MATLAB or Simulink, right? So we love Simulink because they give us a very high level representation of the system. So one of the ideas that came lately is actually to design. So if you do something which you've done optimization in operation research, as I've done, then you run into things which are called ample and GAMS, which are sort of high level ways to represent optimization problems in such a way that they compute the Hessian for you when they feed it to an optimization solver. So if you want productivity and you're a system analyst, you do need to spend time, invest time in architecting this layer where you're actually going to instantiate your abstraction. For example, where you're going to compute the Hessian of the optimization problem. That turns out to be where you spend most of your time, not in the solver. So one of the things that we've done is actually that there was this, I'm sure you guys have heard about Julia. So sort of like, there's this new language, Julia, which actually made optimization extremely easy because there's somebody who created this environment called Jump. What JUMP wasn't doing at the time is that it was not doing parallel instantiation. So we were in this situation that it was taking us an hour to solve the problem and 5 days to instantiate it, because we had to instantiate each scenario in serial. So we actually provided a new environment where we can instantiate nonlinear, non-convex problems in parallel. We've done it in Julia. Without anything like this, the computation would actually be impossible. What exactly we've done would take a bit of time to explain. But we have an environment in Julia which actually has the blessing of being very compact. So for example, the problem which I showed you on the first slide fits in a page now. And it's with full algebraic description. All the equations are here. So, a problem with 10,000. So, of course, there's a big for loop here somewhere. But the point is that, like I said, this is all free and fast and instantiable in parallel. If you get a commercial solver like Ample, you cannot instantiate in parallel. So that's actually one of the places you lose. So anyways, summary. We manage the grid very well today, but it's not a solved problem. On top of that, we have a grid which will change dramatically in the next 15 years, and I don't think we're prepared to address it unless we spend some thought about how we're going to do it. This will change our analytical abilities multiple levels. We actually need to think about the mathematical foundations quite a bit. And again, as I said, what is practical sequential decision making without certainty is something we have never really done. So if you look about what's done, it's a small subset of what we need to do. So that's actually something that we've never thought about how to do at scale here. Certainly there's a lot to still be done about probabilistic modeling, and I gave you one example. There's a lot to be done about new algorithms, again, for reasons you may not expect, just because of the way the information flows in a computer, as I gave you the example before, not necessarily because the algorithm has theoretical bad bounds. And there's issue about problem representation. If we're serious about solving systems at scale, we're going to have to spend time thinking about how do we come up with this representation which are universal and scalable. That's all I have to say. Thank you.
Questions for the speaker?
Yeah.
So you've mentioned that when you introduce wind and solar into the equation, that you have additional uncertainties due to weather. To what extent would having those powered batteries and have the batteries interface?
I get this question a lot, right? You're right. That would change things completely. Right, that would change things. So that's right. So having large, inexpensive storage would change things completely. So there's other things which will change things completely, and people are talking about microgrids. So yes, that will change things completely. This problem will likely not be applicable anymore. So it's a fair point. What I can say at the moment is that I don't see, say, in the next 5 to 10 years, that kind of penetration of storage that would just say. So, for example, so wind power in the U.S. is almost 5 to 7%, I think, of overall budget, which is high, actually, if thinking where you start from. I don't see battering having that kind of commercial impact. But if they do, you're right. So that would certainly change. That would certainly. I'm talking about mass batteries, right? So I'm talking. If they do, we'll have to change things completely. However, what's interesting, we may have to change them still at the consumer level, not so much as the. So that may change the economics. So here's what's going to happen. So let's say somebody gets batteries, right? They put them in their house, which is what. So remember, I had one such example, right? So for instance, this example had a battery. Yeah. Right? So what you observe that even with that one, right? So I mean, and let's assume they have a solar panel too, right? Even with this one, it doesn't mean that you may not have, you may be able to cover all power necessities, say, for a year. So just the battery in itself may actually not solely accommodate the problem. So that's a part of the answer. This was not a small battery. The only question is that how much storage will you have available cheaply? And that will govern what the answer is, whether the grid is going one or the other. Let's say the large amount of storage will be done cheaply. Then pretty much everybody will disconnect from the grid. And we're not going to have the grid anymore except for very large consumers and very poor ones. that will make it for a very different problem. And I agree this would not apply. All I can say is that we thought a bit about it, and certainly there are circumstances where it's worth still doing optimization uncertainty even when you have storage. But you're absolutely right that the consequence of how many scenarios and how you do it will change completely. That I agree. That's true. Yeah.
So some of the discussion that you had was assumed that the grid takes on the year.
Right.
Especially in the distribution level, would you say there is any future for decreasing the amount of uncertainty by imposing on the customer
Right.
certain rule patterns that we can impose?
It's a great question. So this is, so people, oh, I'm sorry, you're right. I forgot about that, right? So the question was the following. So this is, my argument was that if you allow for a lot of load, a lot of the power supply on the grid to be, particularly at the consumer level, to be from solar and wind, you can do two things. One of the things you could do is actually to put very strict restrictions, or actually say be more clear about how that resource can be used by the operator, which is the homeowner. And the question was whether that's possible. The answer is that's certainly possible. And you can put the rule of nobody should install anything. But politically speaking, it's not tenable. Right? So sort of like, I don't know who will vote that law and stay in office. So and sort of like, the reality is that for example, the reliability constraint I show you, it's regulatory. Right? So the regulator comes and say you should do this. Nobody likes a regulator, but they're federal. Now, if somebody does that, it has to be at the level of each state. So you know that individual personally. I mean, right? So it'd be very different dynamic, social dynamic. However, most likely what's going to happen is that there's going to be a line draw somewhere in the middle. I don't believe there's going to be no restriction on what you put on the grid. But I don't think it's going to be severe. What it is, I don't think anybody knows. So let me give you an example. So one of the direction the grid is going, one part of the discussion which is driving the energy discussion right now is actually what happened in Florida last summer. So probably more of a driver is not cost as it is the notion that when something bad happens, like a hurricane, you can recover as opposed to 10 days as we saw in Florida, which is pretty damaging, to recover in a day or two, guaranteed in 100. So then there's the issue of microgrids. Microgrids are really interesting beasts that you can have a whole neighborhood to decide to attach and detach from the grid. We don't have even a rule for when that should happen for reliability purposes. Like FERC doesn't have an opinion, right? So normally it's NERC or FERC who would impose a rule. They don't have an opinion yet. So what's happening is that they're having people like me run studies and take it all in and present it to the commissioner and making a decision. That's what's likely to happen. My guess is that we're not going to get to strict rules at the consumer level. What could happen is that we're going to get these local aggregates, probably with microgrids, and those may be tightly regulated, but not at the consumer level. That's a guess. Also because I think technically it's feasible. So it turns out that what happens is that if you have the resources of a whole neighborhood pull in and get some local storage, some distributed storage, you can actually stay about a day just fine. It would not cost even that much. Now, you'd also have to probably negotiate with each individual owner, what their air conditioner is, but that's doable. And there is the software to make this decision. Or we can make it. It's a lot harder at the individual level.
But especially if you have these aggregators, then the amount of uncertainty you have to deal with will reduce a lot.
Absolutely. That's why I believe it's going to be the way to go. So
And that might be cheaper electricity.
correct. So personally, I believe that in the long run, there's not going to be a grid. That's my personal opinion. And long run can mean 20 years. I mean, there will be a piece of a grid here and there. I mean, there's big utilities like, they're aluminum plants, right? They're not going to create their own energy online. It's impossible. But they may be the only customers, right? So we may get, because like I said, if you look, so here's actually an interesting factoid. To build but that's about gas plants, which is another disruptor. I'm sorry, the wind plants. So wind plants in the Midwest are cheaper to build than any other plant except gas. And gas is cheaper because the price is very low right now. And that can fluctuate. So, how expensive it is to build, So the cost of technology, though, is primarily wind, not solar. Solar is still kind of, but the energy is going to a place where actually having your own generation, which is clean, is going to be quite affordable. I just don't see how, you know, you're going to want to stay on the grid in that circumstance. And the only reason would be reliability. And probably what you're going to want to do is that your neighborhood is connected so everybody goes to one battery or some sort of insurance. And that will be local. But I doubt the need for a real backbone in the real long run. Very few people agree with me, but that's my opinion.
I think we're way past 5 o'clock, so let's
Right.
take the speaker.
Thank you.